Thank you.
Thank you very much for kind introduction, and thank you for the organizer for the kind invitation. I was looking forward to attend the conference in person, but we heard from the previous speaker that travel happens in these days and unexpected schedule change, so that I was not able to attend in person. Hopefully, in the future, I will have an opportunity to attend in person to this very interesting event. That's I've been hearing different types of chemistry. Just we heard about nuclear waste chemistry using plasma treatment. So the topic we are going to discuss in my presentation is focusing on the battery cathode material, the solid state electrochemistry, and rational design is the designing material based on the quantum mechanics simulation based on density functional theory. That's the basic core part of the presentation. And I will briefly mention toward the end of the presentation how we are going to take this design to actual synthesis and experimental development of making cells so that the complete the process of designing novel cathode material to address one of the key issues of the battery capacity and cycle life issues based on our understanding of solid state electrochemistry and current process of experimentally validating that theoretical analysis and then subsequent development into actual battery cells, accelerating whole battery development cycle. So this is part of the Beacon Center the activity, which is funded by DoD, and certainly I'm a faculty member of Material Science and Engineering Department at UT Dallas. Okay, it's moving. So rational design of battery cathode material. So here is the kind of snapshot. So I presume that most of the audience heard about batteries, but may not have detailed knowledge about what is the current status of battery cathode technology. So I'll give a brief overview of the status of cathode material development over the last more than 3 decades. The current commercial lithium-ion battery formulation and technology development started 1991. That's when Sony has introduced current formulation of lithium-ion battery using lithium cobalt oxide as a cathode material, graphite as anode material, and organic liquid electrolyte as ionic conductor. So that's the formulation developed 1991 as a commercial product. Over the last more than 3 decades, it has been extensively improved. The main part of the lithium-ion battery improvement was driven by cathode material, because cathode material represent about half the cost of the battery itself. That lithium being expensive material, cobalt and other transition metal being expensive part of the material, and graphite is less expensive, organic liquid electrolyte less expensive, and the remaining part of the battery is the packaging of those batteries. So energy density cost of the battery, lithium-ion battery, driven by cathode material energy storage density. Starting from lithium cobalt oxide, and over the last 30 years or so, there's extensive development of energy density, gravimetric, the energy density watt hour per kilogram, or volumetric density, because we are densifying the material. It's been increasing, and it has gone on, and then right now it's about 300 watt hour kilogram. That's a current status as we, and certainly depending on the choice of the different electrode material, especially anode material side, that lithium metal or other types of anode material, silicon anode can change different energy density. Those are technology under development. The mainstream, the lithium-ion battery produced in the volume of terawatt, multiple terawatt hour per year is mainly based on this lithium-ion battery, lithium metal oxide, this cathode material, graphite, liquid electrolyte. So that's the main battery chemistry and how this evolution has been happening over the last few decades, and what are the current status of issues, and how we design the material to address these issues. That's the main focus we are going to cover now. Let me move to the next slide. Here is a snapshot of the lithium-ion battery energy density, even cost. Half the price of the lithium-ion battery cell is the cost of the cathode material, assuming that we are using layered oxide transition metal oxide. Uh, some of you may heard about lithium iron phosphate that's not including this expensive metal, then this changes and overprice also changes. But let's focus on this mainstream layered oxide. So we call this layered oxide because the transition metal in the first generation lithium cobalt oxide. This is all the transition metals are only cobalt. The cobalt oxide is octahedral bonding. Cobalt oxide is sitting in metal oxide layer, and then alternating layer of this lithium metal, and these metal oxide layers are tightly bonded, and lithium layer is rather loosely bonded, so the lithium ions are going in and out. So that's the intercalation compound. The binding energy of lithium to this interlayer space is about 4.2 volts, to 3 to 4.2 volt. That's determine the lithium-ion battery voltage, which is 3.7 volt in general. So, so that's the basic chemistry. And when we use lithium cobalt oxide, we can use about half of the lithium, so that the theoretical capacity, so-called, is about 280 milliampere per gram of the cathode material. But if you take half of them, which is 140 milliampere per gram, this material becomes unstable. That if you remove this lithium ions, the cobalt tend to move and then tend to change phase change. So that over the last 30 decades, there's a gradual evolution of the cathode material, which is by increasing the content of the nickel and adding some manganese. So the manganese stabilizing the structure, cobalt is still maintaining this layered oxide, which is initial lithium cobalt oxide. Nickel was added to increase the capacity. Nickel has double redox reaction. Nickel in this formulation, as you can see, nominally lithium is 1 plus, nickel, cobalt, mangan overall average is 3 plus, oxygen is 2 minus, so that those 3 plus charges stay, but mangan is 4 plus, nickel is 2 plus, so the nickel can go to 2 plus, 3 plus, 4 plus during the lithium the intercalation, so that it has higher redox capacity leading to higher energy density. So starting from about 140 to 150 ampere per milliampere per gram or ampere per kilogram of lithium cobalt oxide, as we increase the nickel content, energy density is moving toward 230 milliampere per gram out of 280 milliampere per gram. So then the capacity is moving towards 70-80% of utilizing the lithium content, so that as you increase the capacity of this battery for the same weight, of course, we want to use higher capacity, 50% more energy when you are using cell phone. You want to use the same weight, same volume, the battery, but it has 50 times more, 50% more energy inside it. So that's what has been driving the whole lithium-ion battery chemistry, and that's what dictated by the uh, cathode material energy density because of the overall packing density of the battery cell itself. So that's the whole point. But now, as we move, follow the evolution that increasing nickel content and introducing mangan. So first one introduced was nickel, cobalt, mangan, one third, one third, one third. We call this 111. That becomes very stable. Capacity becomes about 170, so it's increasing about uh, a little bit more than 15%. And then increasingly just NCM, nickel, cobalt, mangan, the relative ratio 50%, 60%, 70%, 80%, 90%, now approaching 100%. This is where the current commercial product, about 80% nickel and some high nickel cathode material have 90 or even 95% of nickel concentration. At that nickel concentration, nickel ratio in this layered metal oxide, the capacity is beyond higher than 200 milliampere per gram or ampere hour per kilogram. So we are increasing the capacity, but there are other issues accompanying this increasing density. So let's take a look at what are those issues and how we address those problems. Before we do that, see, I mentioned that a large part of the research was based on rational design, which is using computational tool based on quantum mechanics simulation and solving the density functional theory. But before taking the interpretation of those simulation data, we need to have a careful comparative analysis with experimental data to validate the accuracy of the simulation. Otherwise, simulation data may not represent reasonably accurate property of the actual physical material system, the solid state chemical, electrochemical property of the cathode material. So this page shows actual experiment we have done to compare with the modeling data. On the left-hand side, this is the NCM that 50%, 70%, and different cathode material. The data point dot is theoretical point, and this gray, a little bit shaded, the data point is GITT, galvano intermittent titration. That's based on the experimental measurement. So that if you compare this experimental data with modeling data, they can differentiate about zero point 0.1 volt of change in experiment in theoretical modeling as well. So this gives us a level of accuracy. There are internal limit of DFT modeling accuracy above 0.1 volt. That's consistent with experimental voltage change while we are de-intercalating lithium ion. So this gives a level of confidence we can predict. And on the right-hand side, what we are showing is that as we go through the cycle life, that cathode materials are going through slight capacity degradation, which is main part of discussion, why capacity is changing, what is going on, how we address this capacity change problem in lithium-ion battery cathode material. But this experimentally showing these changes, and this theoretical analysis shows the level of confidence that we can predict, understand the material behavior and their change with reasonable level of accuracy at the level of less than zero point 0.1 volt. So here is the actual stability map we have developed about 10 years ago, 2016. This published in Journal of Physical Chemistry at that time. So this is mapping out the stability, as I mentioned, that initial cathode material, Sony lithium-ion battery was using lithium cobalt oxide, and later on, next generation is one third, one third, one third. The ternary phase diagram is reading that this pure lithium cobalt oxide, pure lithium nickel oxide, pure lithium mangan oxide, this color map shows relative stability compared to isolated, phase separated. So, for example, if you look at this data point, one third, it shows about uh, boundary of this about minus 20 kilojoule per mole. So if you have a 3 mole of material, this material is 20 kilojoule per mole more stable than as a compound of mixing this cobalt, nickel, mangan in the metal oxide layer rather than having three separate phases. So that's what this phase diagram represents. But as you can note, that lithium mangan oxide is not very stable because mangan favorable oxidation state is 4 plus. Lithium nickel oxide is marginally stable. So the cathode composition evolution over the last 3 decades was starting from lithium cobalt oxide, NCM111 is here, and then nickel rich concentration is following this trend line. So most of them are stable, become less stable, and as we approach the 75%, so 87% along this point that becomes less stable. And how do you understand this was, and this is assuming so-called solid solution model. We'll go through that. What is the limitation of such model and why this becomes an issue from experimental point of view, how we do the theoretical analysis to understand. Understanding this material is not easy, as we discussed in the metal oxide layer, that there's a nickel, cobalt, mangan, there's a mixture of three metal elements in this octahedral configuration. But that sounds complex enough, but actual complexity is more than that. Here is what we are going to describe how we get this, and we'll go through a little bit more details of this analysis now. So in this layered metal oxide, nickel, cobalt, mangan oxide layer, this if we take one layer and you get from the top view, the metal coordinated by 6 oxygen atoms, and 3 of them are in the top of the layer, 3 of them are bottom of the layer in that structure. Then this octahedral configuration, then they are neighboring hexagonal network of metal atoms and bonded by these oxygen atoms. So this is showing, first, there are 3 metal atoms, so 3 metal elements are randomly distributed with corresponding elemental ratio, this 111, 211, and 611, 811, different ratio. And there are multiple atomic arrangement. So this is complex enough how to handle if you have pure lithium cobalt oxide, all the atoms are cobalt, so that is pretty fixed, much fixed. But if you have multiple elements, then you have to consider many possible configurations. Even more complex than that is transition metal atoms are known to have multiple oxidation states. The reason why we call this electrochemistry is chemical properties are coupled to electronic state. For example, the representative example, NCM, this is a different nickel cobalt mangan oxide layer. And if you choose nickel monoxide, nickel is 2 plus, oxygen is 2 minus, so nickel atoms are in 2 plus charge state. Some of the nickel atoms, electron structure comparison shows that actually some nickel atoms are showing 2 plus charge state cation electron structure. If you compare this, some nickel atom, then lithium nickel oxide. This now in this case, nickel is in 3 plus charge state. Sorry, that's that. And in this case, the last one is nickel is 4 plus charge state. Depending on the choice of, this is not deterministic in our specific arrangement. Atomic arrangement are changing, and in that arrangement, depending on the location, same nickel atom can be 2 plus, 3 plus, 4 plus. Cobalt atoms can be 2 plus, 3 plus, 4 plus. This becomes rapidly very complex problem to address. So, to address this problem, we have done systematic DFT simulation of this analysis and do careful the effective metal-metal interaction analysis leading to this metal-metal effective interaction in NCM cathode material. Based on that, we can see that some combinations are favorable, that introducing of manganese 2 plus is favorable, manganese 3 plus is not favorable, nickel 3 plus is not very favorable, nickel 2 plus is favorable. All these are coming out of this. Based on this, we can now map out the stability diagram. As I said, there are multiple ionic configurations. We are using cluster expansion. So this NCM111, and there are multiple configurations. And search it through this atomic configuration space. And this is the lowest energy configuration. Usually they tend to be solid solution. And this PS is phase separation. When you completely phase separate, that's the reference. You have 2 or 3 separate oxide phases. And when you mix them, because of the chemical affinity of different components, you have tendency of improving the stability. But something interesting is happening in this area. I mentioned that as we increase the capacity, utilization of the lithium is approaching 70-80%. Nickel is also approaching 70, 80, 90%. 811, nickel 90%, high nickel. So there, what this indicate that as we increase more than 70% nickel in the cathode material, this star solid solution, random mixing of atoms, is less stable than this cluster calculation. So we look into more details of this part of structure. Then when we look into this part, there's something else. So what we are plotting this color map is assuming solid solution, this star, but as you see, there are something else is happening as you go to higher nickel concentration in this part of the phase diagram. So if you look at more carefully, that this is full DFT modeling data, then if you look at solid solution, then beyond 75%, the solid solution is less stable than clustering. So it's driving that there's a rapid transition for this random alloy of nickel, cobalt, mangan element in the nickel-rich mixture of the cathode material. When you increase the nickel concentration beyond 70%, those cobalt mangan atoms tend to cluster them, phase separate. They are minority species, but not just minority randomly distributed, but they're precipitate so that effectively overall material behave like phase separated material with nickel, lithium nickel oxide. So abrupt change of the material, more than 75% of the nickel concentration is rapidly behaving like a pure lithium nickel oxide. that is source of a lot of challenges and material property evolution. So here is the actual practical issues we have addressed. That when we make the material, of course, everything is finite, so that there's a finite typical size of the cathode material particle 5 to 10 micron. There are surfaces. The surface, typical NCM cathode material surface is supposed to have corresponding elemental ratio, but if you compare that with pure nickel oxide surface is more stable than NCM mixed metal surface, leading to that the surface will be nickel rich. So from the surface point of view, cathode material is behaving like pure lithium nickel oxide. So then if you look at that part, the driving force is that on the surface that nickel-nickel interaction is more stable than nickel-mangan, nickel-cobalt. That's the basic reason we have the previously mapped energy diagram. Based on that, we can look at the surface energy and shape evolution. All this is showing without getting into too much of that, leading to this surface phase evolution that nickel oxide. So you see that this oxide layer was lithium metal O2. But to form this rock salt phase, the surface metal atoms are moving, not only moving, but also you need to adjust the stoichiometric ratio of this metal oxide into metal oxygen 1:1 rather than 1:2. So you have to have a oxygen loss, oxygen evolution. So that's the part of the problem, degradation mechanism of this. The nickel-rich cathode material surface is behaving like a pure lithium nickel oxide. So this is based on that, this actual experimental data we have obtained using pure lithium nickel oxide. We have done the synthesis. If you do the 100 cycle, overcapacity is rapidly degrading. This is, of course, well known in the community. So this is not the first time we are showing that, but the point is that we have done the theoretical analysis and corresponding characterization and what's happening on this, so that at the surface, that when we delithiate, the metal atom tend to come out and forming more rock salt-like structure. To facilitate that, oxygen atoms are evolving from the surface and end up forming rock salt phase. So that half of oxygen atoms in this, when you remove lithium, nickel oxygen 1:2 ratio become 1:1 ratio. Half of the oxygen atoms from the cathode surface is evolving into oxygen gas. This is a serious source of the safety problem of battery material. Yes? So here is the actual experimental data showing that when we do this grazing angle X-ray analysis to show that inside of the cathode material, the elemental ratio, initial and cycle, and the surface, so that bulk inside is maintaining 1:2, roughly 1:2 ratio, but surface is turning 1:2 ratio to 1:1. So there's turning the surface into the nickel monoxide rock salt phase, which is not ionically conducting, so that this rapid degradation of material is driven by conversion of the surface layer into the inactive nickel monoxide layer. So this has two problems, that inside of the cathode material is not accessible because nickel monoxide is not ionically conducting. Second problem, more serious safety problem, is oxygen is evolving, so that when we use battery, there is a waste heat because electric energy utilization is 100, not 100% efficient, so that 89%, the remaining electric energy is turning into waste heat. So that's the reason why battery is heating up. And organic liquid electrolyte is hydrocarbon. So inside the battery, now you have oxygen, heat, and fuel. So when your battery management is not fully operating at some point, that they may end up starting the combustion reaction, the thermal runaway reaction, then without having anything else just inside the battery has all the ingredient to initiate that spontaneous fire. That's how lithium-ion battery fire is happening. That it is related to high capacity cathode material, tendency of oxygen evolution, and certainly we want to use a lot more energy density for the given material. That's the challenge we are facing. So according to this, if we can protect the surface. So we have developed a surface stabilization scheme that by have oxide coating, we protect the surface and suppress this nickel monoxide formation and oxygen evolution. We can stabilize this and actually suppress this battery degradation and a safety problem. But the second issue is that actually even if you do the coating of the cathode material, the cathode material itself during the charge discharge cycle, it goes up to 6% of volume change. The oxide is ceramic. Ceramic is a brittle material. So the typical macroscopic brittle material fracture strength is about, if you have a strain 0.1%, then you tend to break. 0.1% of strain, volume-wise 0.3%, but this is substantially higher than that. Typical glass breaking, the ceramic breaking strain. So that it's not surprising that during the cycling, the ceramic particles are breaking. Well, the point is that even if we do this type of coating to stabilize, the particle is breaking, exposing new surface, which will be prone to have same oxygen evolution problem. So the root source of the problem is actual volume change. This is the reason why when we use lithium-ion battery in our cell phone, over the time the capacity is going down because cathode material over the hundreds of cycles is going through this fracture and exposure to liquid electrolyte and degradation and losing the capacity as to a lesser degree, but uh, qualitatively same mechanism. So the next problem, how can we address this problem? Because this is the source of the problem of each cathode particles is going through the mechanical deformation, going through the fracture, liquid electrolyte penetrating, and on the surface, nickel monoxide like phase is forming and losing the capacity. This is a kind of uh, the conventional, typical process of capacity degradation. So how do we address this problem? So in order to address that, the next thing we have done was how to control the volume change. So I think I'm a little bit, uh,
Dr. Dr. Chair, kindly
yes,
conclude the
sorry,
please.
sorry, can you repeat?
Yeah. You take enough time to conclude it, but keep the
Yeah,
time limit
yeah,
in your
I'll
consideration.
finish in 5 minutes. That's
Okay. Thank you, sir.
So this is the kind of phase change happening so that we have done this analysis and to do that, what's the source of the mechanical change? And we have done analysis that in plane strain, out of X plane strain, And based on that, we look into the phase change problem and how the volumetric change is happening between H2, H3 phase formation. And we have looked into that, and source of this volume change is coming from this part. When you have the more than 70% lithium utilization, you begin to have rapid volume change. That's the source of the mechanical pulverization and cathode degradation. So we looked into that, and this mechanical property analysis and electronic structure analysis. Based on that, we developed a design strategy to suppress this volumetric change using so-called pillaring element. When we introduced pillaring element into the lithium layer space between the metal oxide layer, then here's the summary of our finding that without pillaring element, lithium nickel oxide volumetric change is happening rapidly over the 70%. Depending on the choice of this element, actually we can practically achieve zero strain cathode material. So this is essentially solving the source of the problem, that you can suppress the volumetric change if the shape change is still happening, but you can substantially reduce the mechanical strain driving the degradation of the cathode material. And that's the summary of this finding by introducing these different pillaring elements. And this is illustrating the point that how introduction of pillaring element with pillaring element, without pillaring element, how the strain evolution happens in the polycrystalline cathode material sample. So this work was published, and this was a news article. This is a student who has done the work. He is now currently working on the follow-up experiment. So based on the design, he is developing this rapid prototyping synthesis using robotic arm, high throughput synthesis method, and using Beacon Center facility. We are planning to eventually scale up this to produce cylindrical and pouch cell, so that this starting from the material design all the way to high throughput synthesis, and this is a long way to go. That I'm showing the theoretical design, and experimental synthesis on the way, and eventually we want to scale up and rapidly validate in the experimental cell format. So these are the overall publication over the years, and there are different members contributing to this work, and there are different funding sources. And he is a person who just finished his PhD a couple of months ago, and I'm happy to answer any questions. Thank you.